Thanks everyone for joining. Professor Van Wyk, thank you as well for joining us. So today we'll have Dr. Liam Baker, who is one of our new professors or lecturers at the university, right?
Yep.
So he'll be giving us a talk today about the Lucas's theorem and then how that pops up in our blood pipes. I don't know anything more. So with that, Liam, I give it to you.
Cool. Hi everyone. Lucas's theorem. Lawrence mentioned the first subtitle having to do with blood. There's another subtitle which I'll write here as well. Generating functions are cool. Because they are. Anyway, Lucas theorem. What is Lucas's theorem? Before we get to that, I'll just give a quick reminder of how of some modular arithmetic and some binomial coefficients. You should hopefully know this, so I'm going to speed through this very quickly. You should remember that there are these binomial coefficients. The South African usually use the notation m choose n, which is the number of ways to choose choose n items from a set of m items. Cool. That's the one definition for it. There's also an equivalent formula in terms of factorials. M factorial over n factorial times m minus n factorial. Cool. And a brief reminder on what modular arithmetic is. So the notation, this would usually be for integers. We would say that one integer is congruent to another integer modulo the third integer m is the same as saying that your m, which is called the modulus, divides the difference between a and b. So in other words, a and b have the same remainder when you divide by m. In the talk today, we're only going to be considering mod a prime p. You should, I'm sure you know what a prime number is. A different notation. When I was in high school, I learned the notation a congruent to b, then with a subscript p, which I'll be using most of the time now. It's not much of a difference.
Herman, al vanoggend gestuurd.
Cool. So we have the binomial coefficients and we have modular arithmetic. You should, I'm sure you know modular arithmetic and the different properties that it has. And now we can finally state Lucas's theorem, which is kind of cool. I think it's cool. Anyway, if you have a number, let's say m, and I'm going to write down the base p expansion of m. So p is a prime number, 2, 3, 5, 7, any prime number, and I'm going to write it out in base p. Let's write it like mk is the kth digit, p p to the k plus so on up until m1 times p plus m0. Different notation for base p you might be used to would be just writing the digits, nk, and so on till m1, m0. So m0 is like the units digit, then with a line across it, I think that's the notation some people use, with like a base p or something like that. So if we have one number written in base p and we have another number written in base p, so the same thing, up until n1p plus n0 times p to the 0. So this is also written in base p.
Can I just stop you there, Liam? It
Sure.
seems that it's not scrolling down on my side.
I think you can move the whiteboard around on your side.
Oh, okay.
Yeah, so everyone might have to just move the whiteboard for themselves, but then they can also move back up to look at previous stuff.
Yes. Okay.
Cool. So if we have two numbers written in base p, then, so these could be very big numbers. We can consider the first number the binomial coefficient, or the first number over the second number. And Lucas' theorem tells us what this is modulo p, or what the remainder is when you divide by p, and it's actually quite nice. Oopsie. It's simply the kth digit, so the binomial coefficient formed by the kth digit, multiplied all of those together, m1 choose n1 times m0 choose n0. So we actually just take the units digit and form the binomial coefficient from those. And we take the, well, what we usually, when in base 10, we would say the tens digit. We take those digits and take the binomial coefficient formed by those, and we do that for each pair up until the leading digit, and we multiply all of those binomial coefficients together, and that is the remainder of our big m choose n modulo p. To illustrate, let's do an example. Oopsie. Let's do an example. Lawrence, could you give me like maybe two-digit numbers?
Okay.
A small prime.
17 and 73.
17 and 33. Okay, so 33, choose 17. We want to know what that is modulo which prime. Let's do, shall we do 5? Yeah, let's do 5. Okay, so if we want to do this, we need to write 33 in base 5. So the biggest power 5 below that is 25. So that'll be 25 plus 15, no, 25 plus 5 plus 3. So that'll be 113 in base 5. 17 in base 5 is 32. But in fact, yeah, for Lucas's theorem, we need to have the same number of digits for the top and the bottom. So 17, the 32, we can just add a 0 at the start. So 113 base 5, 032 base 5. If we evaluate that, base 5, that'll be 1 choose 0 times 1 choose 3 times 3 choose 2. Good. Now the 1 choose 0 is just equal to 1. 1 choose 3, because 3 is bigger than 1, that's equal to 0. And 3 choose 2 is 3, so that's 0. So this 33 choose 7 is 0 modulo 5. In other words, 5, because it's a prime, divides 33 choose 17. Cool. So if you didn't know, now you know that 5 is a factor of 33 choose 17. Let's do another one, another example. Let's have maybe 2 3-digit numbers. How about Rolf? 2 3-digit numbers for me.
3, 2, 1, and 1, 2, 3.
Okay. So now we're asking, what is the last digit of 321 choose 123? Yeah. Now, whenever we ask for the last digit of something, it's the same as asking what's the remainder when you divide by 10. Now, the thing is that 10 is not a prime number, so we can't use Lucas's theorem directly, but 10 is equal to 2 multiplied by 5. Both of those are prime numbers. So what we're going to do is we're going to do Lucas's theorem for 2 and for 5, get those two answers, and then put them together to find out what the last digit of that binomial coefficient is. Good. So we're going to need to write 321 and 123 in base 2 and base 5. Okay, so 321 in base 10. That last one is a bit weird. In base 10. If we want to write this in base 5, the biggest power of 5 is 125. So that's 250 and 71. Another 2 for 1 base 5. If I'm calculating these base 5 or base 2 expansions incorrectly, someone please tell me. So that's if you write it in base 5, and 123, well, which we usually write in base 10. If you want to write that in base 5, that is 2 less than that. Should be 4, 4, 3 base 5. And just to make sure that we have the same number of digits on each side, we add a 0 in front of the base. Base 5 expansion of 123. So 321 choose 123 modulo 5, that's going to be 2 choose 0, 2 choose 4, 4 choose 4, and 1 choose 3, which, because 2 is less than 4, that's 0. So this binomial coefficient is actually divisible by 0. It's probably going to be the same thing for base 2, but let's just check. So 321, if we write that in base 2, what is that in base 2? Okay, 256, 1, 0.
So it's 101 and then 5 zeros, 1.
Another one? Yeah, another one, and then 1. Okay, and 123, if we write that, sorry, that's base 2. If we write that in base 2, that is 5 less than 128. Yeah. That's going to be 1, 1. Wait, no, that's not right. Okay, that should do it. I hope that's correct.
It is.
Okay, we need to add 2 zeros at the start. Similarly, before, we can 3, 2, 1, choose 1, 2, 3. If you want to do that mod 2, that's a bunch of stuff, but it's easy to see that at least one of those is going to be 0, choose 1, so that's 0. So in this case, we have that 5, 5, and 2 are both factors of 3, 2, 1, choose 1, 2, 3. And because 5 and 2 are relatively prime, 10 is a factor of 3, 2, 1, 1, 2, 3. Factor of. So the last digit is a 0. Cool. Great. Okay, so that's some examples of how to use Lucas's theorem. I'm going to try and do a quick proof of Lucas's theorem, and then I'll show you what this has to do with our blood. Okay, so how do we do Lucas's theorem? I'm going to use some modular arithmetic with polynomials. And what that means is I'm going to have some polynomials, a of x, b of x, etc. are going to be polynomials with integer coefficients. And when I say that one polynomial is congruent to another polynomial mod a prime number, what I mean is that each coefficient is congruent to the corresponding coefficient on the other side. Let's see, corresponding. So the constant term for A is congruent to the constant term for B. The linear term for A is congruent to the linear term for B, and so on. Okay, and you can be sure that, like, if you add two polynomials, each of which is congruent to another one, you can just add on both sides. You can multiply polynomials and it behaves the way you would expect modular arithmetic to normally behave. So the first little lemma that we're going to need is that if you take the polynomial 1 plus x to the power of p, that is congruent mod p to the polynomial 1 plus x to the power of p. Cool. And the proof of this is as follows. If we take 1 plus x to the power of p, using the binomial formula, you can multiply this out with binomial terms. So that's p choose 0 is the constant term. Then we've got p choose 1 times x, and p choose 2 x squared up until p choose p times x to the p. Now this first term, p choose 0 is just equal to 1, and p choose p is equal to 1. What we need to show is that p divides each of these other terms in the middle. P choose 1, p choose 2, up until p choose p minus 1. So what we want is that p divides p choose r if r is between 1 and p minus 1. Well, we can write p choose r in our factorial formula. P factorial over r factorial p minus r factorial. So p obviously divides the numerator because the factorial is a product from 1 up until p, so it obviously has p as a factor. And p does not divide r factorial, so this is where the fact that p is a prime gets used. It doesn't divide r factorial because r factorial is a product of terms less than p. And similarly, p does not divide p minus r factorial. This is because p is prime. So p divides each of the terms in the middle. We're only left with p choose 0 at the start, p choose p at the end, and so the lemma is proved. And now we're actually going to take this lemma a little further. We're going to, so that's the base case of the following lemma. So let's call this lemma 2. Is that if I have 1 plus x to the power of, previously we had it just to the power of p. Here we're going to say to the power of any power of p. So let's say p to the L. The same thing holds. So that's 1 plus x to the power of p to the power of L. And I'm not going to prove this lemma in full, but this can be done by induction. on your L, which is starting at 1. When L is equal to 1, we actually just get the previous lemma. Yeah. But when L equals any particular value of L, just uses the previous one, because 1 plus x to the power of p to the L is just the same as 1 plus x to the p to the L minus 1, taking all that to the power of p. So using the induction step, I've changed my mind. I guess we're actually going to do this induction sort of formally. The inside polynomial is just 1 plus x to the p to the L minus 1, and that again to the power of p, and that's by the inductive hypothesis. And then we can use the previous lemma again, because we have 1 plus a polynomial to the power of p. Oh, sorry, this is congruent mod p. Forgot to write that. So we use the previous lemma again to show that this is equal to 1 plus x to the p to the L minus 1, that to the power of p, which is what we want. 1 plus x to the p to the L. Cool. By the way, I forgot to mention at the start, if I'm like going too fast at any point, or if I've already gone too fast and there's a question that you have on something I said previously, yeah, please feel free to like raise your hand or unmute yourself and ask a question about anything that is happening or is going to happen or has happened already. Yeah, please don't hesitate, because otherwise I feel like I'm the only one talking here. I don't want to be alone, guys. Okay. So now that we have this lemma, we have basically all that we need to prove Lucas's theorem. So let's get back to the context of Lucas's theorem. We have M, which is written in base P, and each of those digits are between 0 and P minus 1. So that's each mi is between 0 and P minus 1. And we have the same thing for n. Okay. Now we want to know what is m choose n. That's what we're trying to calculate, at least modulo p. So the key comes in the link between these binomial coefficients and the polynomials I was talking about just now is the binomial theorem, which we used before. Just a quick reminder, perhaps little segue on this side, is that if you take 1 plus x to the power of m for any integer m, and you multiply that out, what you're going to get is m choose 0 plus m choose 1 times x. So we have the terms going on up until m choose m minus 1 times x to the m minus 1 until finally m choose m x to the m. Or in other words, the sum over r from 0 to m choose r, x to the r. So we're going to use this binomial theorem over here. I'm sorry for these like random little lines that are coming over the screen. I'm not really sure where those are coming from. Yeah, but this is my first time actually using this whiteboard on Teams. Maybe it's something to do with my pen. Anyway, so from the binomial theorem, we can see that m choose n is the coefficient of x to the n in the expansion of 1 plus x to the power of m. Cool. So that's what we're trying to calculate. That 1 plus x to the power of something looks familiar. It looks similar to the lemmas that we were doing previously. So I'll try to... So let's use the fact that m has this base p expansion. And also I'm going to use a little shorthand. Not sure exactly how standard this is, but I'm going to use this bracket x to the n, and this is the same as the coefficient of x to the n in whatever follows. Okay, so that's the coefficient of x to the n in 1 plus x to the power of this base p expansion, so mk p to the k plus and so on up until m1p plus m0. So here we have something to the power of adding a few things. So we can, of course, use one of the exponent laws. So that's coefficient of x to the n in 1 plus x to the mk p to the k. So we're going to split each of these up until we get 1 plus x to the m1p times 1 plus x to the m0. Okay. And then each of these terms, we can use the lemma that we have above to simplify it. So this first one, when we have 1 plus x to, so we have mi, because this is the ith digit, times p to the I, that's the same as taking 1 plus x to the p to the I, and taking that whole thing to the power of mi. So that's what we're going to use here. We're going to use the previous lemma where this inside can just be replaced with 1 plus x to the p to the I. So this is then 1 plus x to the p to the k times mk. Sorry, not a plus. There we go. So times, and we're multiplying, and we get 1 plus x to the p to the power of m1 up until the last one doesn't change. Okay, we've made some progress. Now what's cool to notice here, let's write this in red, is that this first bracket only has powers of x to the p to the k. All the other coefficients are 0. And the next bracket, the next bracket will only have powers of x to the p to the k minus 1. And so on with each bracket. And this one, for instance, only has powers of x to the p. So that's the first thing to notice about this expansion that we have over here. Each bracket only has powers of x to the p to the whichever power we're working with. The second thing to notice about each of these brackets is that because these digits, these m0, m1 up until mk, because each of them are only between 0 and p minus 1, this first bracket has no bigger powers. So no powers of x to the p to the k plus 1. Because the largest power here is going to be x to the p to the k times mk. The x to the p to the k, sorry, let me just erase that. The largest power here is going to be p to the k times mk, which is less than p to the k plus 1. And that's why it's important that these are the base p expansions. They have to be between 0 and p minus 1. And similarly, each digit doesn't have any powers that are too big, that actually interfere with brackets which are bigger than them. For example, the second last one has no powers of x to the p squared or above. And this last bracket has no powers of x to the p. Okay. I hope you see where this is going. This expansion into different powers of p, we've proven that, like the first factor, for instance, only deals with powers of p to the k, and it doesn't have any terms that are power p to the k or bigger than that, and so on. Each factor only deals with a specific digit in that expansion, in the base p expansion of m. So when we write that when we write n as its base p expansion, n to the k times p to the k plus n to the k minus 1, p to the k minus 1, and so on up until n1 p to the 1 plus n0. The only way that we're going to get the nk, oh sorry, more correctly, the only way we're going to get this power of p, this p to the k, has to come from this bracket over here. That's the only place you're going to get a power of p to the k in the exponent of x. The only place you're going to get a power of p to the k minus 1 is in the next bracket, which I didn't quite include here. The only place we're going to get a power p to the 1 is going to be in this bracket. And the only place we're going to get this power of p to the 0 is going to be in this bracket here. So what this means is that when we look for the power of x to the n in this product of separate, similar looking binomial terms, we can actually expand this coefficient of that we're looking at. So continuing on from our original calculation, that's going to be congruent, or actually equal, but I'll say congruent mod p, to the coefficient of x to the p to the k in 1 plus x to the p to the k to the power of mk. Actually, I made a little mistake here. That it should be x to the nk times p to the k. So that multiplied by the next term is only going to become from the next factor, so that's x to the nk minus 1 p to the k minus 1. The coefficient of that n1 plus x to the p to the k minus 1 to the power of mk minus 1. And each of these terms are multiplied separately until the last one is just the coefficient of x to the n0 n 1 plus x to the m0. Now each of these we can simplify. That in the first term that we're looking for, everything is a power of x to the p to the k. So this is actually the same as saying the coefficient of x to the nk, for instance, of 1 plus x to the mk. So we're replacing x to the p to the k with x in the first factor. And similarly in the next one, that is just the coefficient of x to the n k minus 1 n 1 plus x to the m k minus 1 multiplied, so on, till we get to the coefficient of x to the n1 n 1 plus x to the m1, and the last term is the same as there. Just not going to rewrite it. Cool. And here we are. Each of these terms is just asking for a binomial. Each of these terms is simply just a binomial coefficient. The first one is mk, choose nk. The second one is m k minus 1, choose n k minus 1. Oh, that looks horrible. I'm going to rewrite that. And each of these terms up until m1, choose n1 times m0, choose n0. Cool. And this use of the reason I call these generating functions is because we're using a function, or what might be considered a Taylor series expansion. We're using a sort of Taylor series expansion, but the coefficients of that expansion are the numbers that we're actually interested in. And by doing manipulations on the function or the Taylor series itself, that helps us do things with the numbers that we're looking at. Cool. Do we have any questions before I move to how this is relevant to blood donation? No, I guess not. I'll just have to switch screen. So the thing about donating blood is that not every blood type is compatible with every other blood type. There's a chart that I'm going to bring up soon. Okay, let's switch what I'm presenting to that. Okay, can everyone see the blood type chart over there?
Yeah.
Yes.
Cool. So only certain blood types can receive from certain other blood types. There are 8 of them in all. So 0 minus can donate to any other blood type, but 0 plus can only donate to AB plus, A plus, B plus, or 0 plus. This is a useful little chart. Unfortunately, I am A positive or A plus, so I can only donate to AB plus and A plus. Sad for me. Okay, so what does this have to do with Lucas's theorem? Well, it turns out that this particular chart of which type can donate to which other type can be phrased in terms of Lucas's theorem. pity I can't take this chart with me, but I'm going to switch back to the whiteboard. Hopefully we get the same whiteboard as before. But anyway, I think we've pretty much run out of time. So the long and short of it, I won't have time to write this down on the whiteboard, is that you can write your blood type in base 2 with 3 digits, and each digit will be either 1, 0, or 1. And whether or not one person can donate to another person can be stated simply as whether or not the one number choose the other number is even or odd. If it's odd, then the one person can donate blood to the other person. But if it's even, then they can't. Oh, the whiteboard is back. Cool. Do we have any questions?
So is that an inherent property of blood types, or is it just kind of magically works out that way?
Unfortunately, I'm not enough of a biologist to understand exactly what makes it possible for one blood type to donate to another blood type or not. But it seems too much of a coincidence. It has to be something inherent in the blood. Jean, you have a question?
No. Just on I think the blood types is if blood has a property that you don't, then you can't receive that. And that's kind of the same as the Lucas thing. I don't know details either though.
Yeah, so in terms of individual digits, like if you have a property, it's 1, and if you don't have a property, it's 0. So a 0 can't donate to someone that has a 1. And another way of phrasing or looking at it is that if you have 0 choose 1, that is 0, which is even. Whereas all the other ones, like 1 choose 0 is equal to 1, which is odd, and 1 choose 1 is equal to 1, which is also odd. So I guess having that particular property could be characterized by having a 1 in that corresponding digit place. And then a question of whether one person can donate to another is just whether that binomial coefficient is odd or even. Cool. If I understand correctly, this recording is going to be available on YouTube or something afterwards.
Yes. Trusting that your recording of the whiteboard was functional compared to the recording of Teams.
I hope so. Cool. Thank you, everyone, for coming. Please invite your friends and stuff.
Thank you very much for the talk, Liam. I enjoyed it a lot. And yeah, next time we'll learn a bit more about biology before we jump into the details why blood works the way it does. Yeah, then without any further questions, I just want to make one small advert announcement before everyone leaves. And yeah, thank you just once again for your talk.
Pleasure.
Okay, so I'm just going to share my screen here. Okay, can everyone see my poster here?
Yep, I can see it.
Okay, so to everyone that's there at least, I just want to remind everyone about the sums committee application for next year. So our committee is finishing up. This is our third last talk. Next week, I'm still confirming, but next week I'm trying to get Pim Boquet, who is a friend of, or a colleague of one of the lecturers at Stellenbosch that I got in contact with. And then the week after next week is our last one for the year, which will be a second round of the honor students presenting their projects. So that Tuesday, the honors are presenting, and then after that, we'll do it for sums again. And after that, we need a new committee. So the positions are still open. I know that it says today is the deadline, but due to some lack of applications, we're going to extend it until next week, so until the 22nd of October. So if anyone is keen for these positions, if you want to know more about it, like what it entails, how much time it takes, any of that, and what we do, then feel free to get in contact with us. Yeah, you can just message us. I'll also put my email available if you want to know more. If you're not interested, but you don't want this society to dissolve, I guess, please do help us out and tell your friends or remind them or share this so that we can keep sums going for next year as well. It's not just students that are allowed to apply. Lecturers are also allowed to apply. Liam Liam could also take up if he wishes so too. So yes, please just share it, or if you're keen, don't mind asking more about the committee. So then, with that, I'll just like to thank everyone again for joining today, and then I hope to see everyone next week again.